Okay, in this slide I have two tables for two different functions, one for f and one for g. And I'm going to go ahead and do a series of calculations, and we're going to notice some things as we do. So f of g of 6, composition of two functions, and we're going to get a numerical value. So f of g of 6 is saying f of, what is g of 6? G of 6 is 4, okay? We look at the table, and f of 4 is going to be 6. G of f of 1. First, find what f of 1 is. F of 1 is 3, so we're asked really to find g of 3, and g of 3 ends up being 1. F of g of negative 4. G of negative 4 is negative 2, and f of negative 2 is negative 4. G of f of 1. Well, g of, what is f of 1? F of 1 is 3, and g of 3 is 1. F of g of 1. G of 1 is negative 1, so we are really finding f of negative 1. And f of negative 1 is 1. And finally, g of f of negative 1. So g of 1 and g of 1 is negative 1. Okay, so we did those calculations, and we're going to be observant. So look what I'm going to do. I'm going to go ahead and erase the work in the middle here. And let's notice something here. Okay? In every case, the input was also the final answer. And in every case, we were first plugging a number into f, and then that answer into g, or vice versa. First into g and then into f. So these functions f and g essentially are undoing each other, right? They're undoing what the other function does, and we end up with the input. Okay? When that's the case, we have a special relationship between two functions. So let's state it down here, definition. All right, if f of g of x is equal to x. So what's that saying? If I first plug a number into g and then plug the answer into f and get out what I put in, and if g of f of x is also equal to x. So it happens both ways, whether you go first into g then into f, or first into f then into g. Okay, then we call f and g inverse functions. They are functions that undo what the other function does. And let's introduce a symbol for an inverse function. So let's see if I can move this over here. Okay, so this symbol right here, f with an exponent of negative 1 of x, is going to be the symbol for inverse function to f. So we'll read this as f inverse of x. Okay, and we have to be very careful that this does not mean, this does not mean 1 over f of x. So this is a case where we reuse symbols in mathematics and they had different meanings. So when you see a negative 1 exponent on a function, it does not mean take the reciprocal. It means the inverse function to this letter here, which in this case is f. Okay, so what does that mean as far as algebraic properties? Okay, it means that if you compose f with its inverse function, you should get out what you put in, which is x in this case. And if you compose it the other way, which is the inverse function having an input of the original function, you should also get out what you put in. Okay? So those are the algebraic properties. We saw them happen here in the table, where f and g were inverse functions. All right, now let's take a look at some geometric properties of inverse functions on GeoGebra. Okay, on this GeoGebra grid, I have plotted the dots that were in those tables on the previous slide. So the red dots represent the function g's points, and the blue dots represent the function f's points. So for example, we have -4, -2 in red, which is on the function g's graph, and then we have -2, -4 in blue, which is on the function f's graph. Okay, and we noticed that in the previous slide that when you have inverse functions, the x and the y values are flipped. Now what I'm going to do is ask GeoGebra to find the midpoint of every pair of points that are flipped. So for example, I'm going to find the midpoint between -2, -4, and -4, -2, and GeoGebra will calculate it and also plot it for me. Okay, so there, right here, it's plotted the points. Looks like -3 and -3. And I'm going to go ahead and do that for the remaining points. So I need to do the midpoint of -1, 1, and 1, -1. I need to do the midpoint of 0, 2, and 2, 0. I need to do the midpoint of 1, 3, and 3, 1. And one more, I need to do the midpoint of 4, 6, and 6, 4. Forgot my parentheses there. Okay. Okay, now if I look at that, I have -3, -3, 0, 0, 1, 1, 2, 2, and 5, 5. So the x and the y values are the same for all those midpoints. Another way of saying that is the midpoints all lie on the line y equals x, which I've just plotted for you. Now I'm going to go ahead and take a screenshot, and then we're going to head back to our document and take a look at something. Okay, so I've pasted in the picture. So remember, we had the red and the blue dots were the function f and g respectively, and I just plotted the midpoints between the points that were flipped, and they all lied on the line y equals x. And now if I rotate this picture so that the line y equals x is vertical, you'll notice that the graph in red and the graph in blue are reflections of each other across this line y equals x. So that is the major geometric property of inverse functions. So let's write that out here. F and f inverse are reflections of each other across the line y equals x. So we know that if 1, 3 is on the graph of f, that 3, 1 has to be on the graph of f inverse. Okay. One thing that's also true, so what we're seeing here is the x's and the y's flip. Same thing happens with the domains and the ranges. Okay, so the domain and the range, whatever they end up being, will flip. So the domain of f becomes the range of f inverse, and the range of f inverse becomes, or the range of f becomes the domain of f inverse. So let's draw some arrows here to make that make more sense. Okay, so the domain of f becomes the range of f inverse, and the range of f inverse becomes the domain of f, and vice versa. So this is a way to find the range of a function, which remember we said was a tricky thing to do in pre-calculus. If a function has an inverse, this is one way you can find the range of a function, is to find the domain of its inverse. Okay, so let's take a look at an example. Let's do a couple things with this function f here. Okay, number one, let's find the inverse function. Okay, so let's find f inverse. Now, I'm going to give you a general procedure here to finding inverse functions. So number one, we will write this as y equals x over x minus 3, because we use y and f interchangeably most of the time. Okay, and then that's the function f. We're going to swap x and y. so that we now have the function f inverse. Okay, so swap x and y to obtain f inverse, at least the relationship for f inverse. So that gives us x equals y over y minus 3, and now we have to solve for y, if possible. Okay, so I'm going to multiply both sides by y minus 3 and hope that y is not equal to 3 and makes this all messed up. Okay, so that leaves me with x times y minus 3 equals y. So I now have xy minus 3x equals y. The trick here is to get the y's on the same side, because that's what I want to solve for. So I have xy minus y equals 3x. I factor out a y, and I'll get x minus 1 inside the parentheses, 3x over here. And so my final line here is that f inverse is y equals 3x over x minus 1. Now, let's write some things over here. So I have f inverse. So f, I'm saying, is y equals x over x minus 3. And I'm saying f inverse is 3x over x minus 1. Let's quickly verify that these are inverse functions. So to verify that I did this correctly, I need to do f of f inverse and then the reverse after that. So let's start here. So f inverse is 3x over x minus 1. So that means everywhere I see an x in the original function f, I'm going to replace it with 3x over x minus 1. So 3x over x minus 1 over 3x over x minus 1 minus 3. Now, this is supposed to simplify to be just x. So that's going to be pretty amazing if it actually does that, but let's go ahead and go through the steps. So this is going to be converted to have a common denominator. So 3 over 1 times x minus 1 over x minus 1 will give us 3x over x minus 1 over 3x minus 3x plus 3 over x minus 1. Here's my compound fraction issue. These denominators will end up canceling. I have a 3x minus a 3x. Those end up canceling. And that leaves me with 3x over 3, which is x. How about that? Now let's test it the other way. So the other way says that if I do f inverse of f, I should also get x. This is how we verify it. So f inverse says take my input, multiply it by 3. So 3 times my input, which is x over x minus 3, over my input, which is x over x minus 3, minus 1. Again, we're going to need a common denominator down here. So we're going to get x minus 3 over x minus 3. Our numerator is going to be 3x over x minus 3. Now we have x minus a negative 3. So that's going to be a 3 over x minus 3. When we flip the bottom fraction to multiply, those x minus 3's cancel out. And we have, again, 3x over 3, which comes out to be x. So we have verified that these are, in fact, inverse functions. So the last thing I want to say is that we are into a world now where we can determine some things we weren't necessarily able to determine before. We could always find the domain of a function like this. Okay, this function has a domain x cannot equal 3 because I don't want the denominator to be equal to 0. F inverse has a domain x is not equal to 1. because again I don't want the denominator to equal 0. Now, what we weren't really able to determine before was what's the range of f. Okay, but because I have inverse functions, the domain of f is the same as the range of f inverse, except we just changed the variable. So the range is going to be y cannot equal 1. So in other words, the range of f is all real numbers except 1. We can never get 1 as an output of this function. That's interesting. And the same thing happens over here. The range of f inverse is the same as the domain of f. So y can be any number except 3. All right, the last thing we're going to talk about is, do all functions have inverses? And the answer to that, unfortunately, is no. Here's an example, f of x equals x squared. Let me show you the problem with f of x equals x squared. Okay, we have negative 2 comma 4 would be on the graph of x squared, and so would 2 comma 4. So if this function had an inverse, then these would have to be flipped. So I would get 4 comma 2 and 4 comma negative 2, but that's a problem because this is not a function. Okay, so functions have inverse relations, but not always inverse functions. So let me show you what happens if we try to find the inverse function, and you'll see the problem here. So we go y equals x squared, we do the variable swap, so x equals y squared, and when we try to solve for y, we get the positive and negative square roots of x, and that's not a function. I would get 2 outputs for 1 input, and if I graph this, I would get a graph that fails the vertical line test. Okay, so kind of the more advanced and kind of the bigger picture is that only functions that are 1-to-1, which means every output has only 1 input, have inverse functions. Graphically, functions that pass a horizontal line test have inverses. So remember, all functions are going to pass a vertical line test. If a function also passes a horizontal line test, it's 1-to-1, and it has an inverse.